Hello students, welcome to class 28. Today we'll go for the next concept of carbonylation. So in the syllabus it is given carboxylation. So make change that it is not carboxy, carbony, that is your insertion of carbon monoxide. Okay, and if possible we'll go for the next to last part of this unit 2, that is organo iron, okay, cobalt and palladium use in organic synthesis. Okay, so this type of organometallic catalyst used in the organic synthesis, that is the last part is there. So if time is there, we will start with one of the organo iron here. Okay, so carbonylation is nothing but insertion of carbon monoxide, in Monsanto process we have used this, okay, insertion, but in that case we have used the first step as CH3I, okay, so methyl iodide addition, oxidative addition into the rhodium catalyst. Okay, so this is which was a rate determining step in Monsanto process, but in carbonylation, so the rate determining step will be oxidative addition of carbon monoxide. So this is what carbonylation, and the catalyst used here is of iridium. Okay, so with iodine and 2 carbonyl here with negative charge, that is your dicarbonyl diiodido dicarbonyl diiodido iridium 1, okay, complex. So this is what is used, and this is nothing but the insertion of CO in methanol CH3. You take methanol OH, okay, and you insert this carbon monoxide into this CH3 OH, that is methanol, in the presence of your catalyst I2 CO2 minus. Okay, so you use this in the presence of promoter. So some promoter is used in this, and a temperature of 150 to 250 degrees centigrade and pressure of about 50 bar. So if you take this, and you are going to see there is the production of acetic acid. This is that carbonylation. Okay, carbonylation, and like Monsanto process. So this is how the acetic acid is produced by carbonylation. So now if you see the catalyst here, so it is of iridium, cobalt, CO, I. So this is a catalyst with negative charge. So like rhodium catalyst what we have used for Monsanto process, so this is what in carbonylation we are using this iridium, which is in +1 state, and this is your square planar structure. And if you see electron count, so 9, 10, 11, 12, 13, 14, 15, and this negative charge, so it is a 16 electron species. Okay, and square planar complex where iridium is in +1 state here. Now if you see the catalytic action of this, okay, so the first step here is as usual oxidative addition step of the methyl iodide here CH3I, and you are going to get as usual the trans addition here, CH3 will be added here and I in this case, and now here CO I. So now see here, if you see the iridium, it is in +3 state, coordination number from 4 to 6, oxidation number from +1 to +3, and this is that's why it is called oxidative addition here. But this is not a rate determining step, as I said in the previous video in Monsanto. So cobalt, rhodium and iridium, so this is very slow. Okay, very fast oxidative addition, and this is 3D is very slow. So that's why, since this is very fast oxidative addition, so this does not become now what you say the the rate determining step here. So this only is a change in carbonylation, that's why it has been fixed into the syllabus here. So understand this rate determining step here. Now this again becomes 18 electron species because of addition of this methyl iodide here, 16, 17 and 18 here. Now next is what, there is elimination of I minus iodide. So this step is done by the promoter, that's why the promoter is used, and usually the promoter used is indium. So this is what iodides in most of the cases, or sometimes the ruthenium complex is used as a promoter here. Okay, ruthenium carbonyl complex is used as a promoter. Indium iodide or ruthenium complex carbonyl complex is used as a promoter here, which becomes this elimination of iodide, and you are going to get now IR. There is CH3 here, then CO, and here there is a vacant created here. Now you can see here there is vacancy is created here because of the elimination of this iodide, and again it becomes 16 electron species. Now it is very easy to addition of the CO here. So now this is insertion of CO, and this step is now RDS. That is what the change here, carbonylation. That is what the carbon monoxide is introduced into here now in this case, and this becomes now that is your iridium, and as usual, so this is your CH3, CO, and here I, like this. Now you can see here there is insertion of carbonyl here, so like this. Okay, again it becomes now 18 electron species, and it remains to be +3 state here. Now finally you can see there is a migration of the methyl group here. So migration of methyl group is going to take place here. Now you are going to see iridium C double bond O CH3, again you are having here CO, again you are having CO, and here I, again you are going to see here from 18 electron you are going to get 16 electron species, and iridium being in the +3 state. Now final is what, there is a reductive elimination. So with reductive elimination, this +3 is going to convert again with +1 state here, and this whole thing is going to be reduced, is going to be removed, and with the addition of I minus, so you are going to get here CH3 COI. Okay, so acetyl iodide is been reductive eliminated, and you can see that the original complex is been availed here. So now final step, that's what in the Monsanto process we have learned, that this is this whatever the acetyl iodide we have reached here, CH3COI is hydrolyzed, and you can see that we are going to get our needed acetic acid along with hydriodic acid HI, hydrogen iodide. So this is what is been formed here, is been done in the cycle. Now if you see whatever the HI is is being produced here, is again react with your methanol CH3OH, and you are going to get your methyl iodide, and this is again step added to our oxidative addition here into this complex here. Okay, so this is how this process is called as carbonylation. So where the carbon monoxide becomes the rate determining step, addition of carbon monoxide becomes the rate determining step, and this is not the rate determining step as we have learnt in Monsanto process. So this is what is the small change here, and the complex also used here is iridium and not rhodium as we have used in you can say in the Monsanto process here. And the first step what we seen here is nearly 200 times faster than the Monsanto. This is what, because we know that this is 3D 4D 3D 4D 5D, always as in the features of oxidative addition we have learned down the group, the oxidative addition increases, okay, faster. So 200 times this is faster here, and moreover this catalyst what we are using is a very selective for the methanol what we are using here. So very nicely there is a reaction, and you can see that the whole thing is going to be promoted here, and the promoter here is role is very much important. Indium triiodide INI3 or sometimes ruthenium complex is used, that is your ruthenium tricarbonyl complex. Okay, so this is used, this complex is used, ruthenium I2CO3 diiodide twice. So this is used, which is going to act as a promoter, so where it helps in removing of the iodide, and even in this case where the same iodide is being again added here to get this acetyl iodide. So this is what about the what is saying. And you can see here CH3I, this I think we have done in the Monsanto process. Here we have learned this. Okay, and whenever this HI and CH3 is been reacted here, whatever the HI is reacted here, so we are going to get here CH3I, and again here we are going to find H2O here. Okay, so this is how it reacts. H2, again this will react with this, this will use this H2, whatever is liberated, again helps for what, for the hydrolysis of this acetyl iodide, again the acetic acid is got. So like this cycle repeats here, and this cycle in the presence of this catalyst is called carbonylation. So this is what you have to keep in the mind, and sometimes it is also called as Kativa process. Okay, so this is what sometimes in some paper they will ask a Kativa process. So yeah, it's nothing but this carbonylation. So this is what about the final part of the organometallic catalysis. Now if we go for the next concept, that is your organo synthesis, in the organic synthesis, use of organic in organic synthesis, use of organometallic catalysis of iron, cobalt and palladium. This is the final part of the unit 2 what we are learning. Okay, so first we'll go for iron. Okay, organo iron. So what is this? This is the iron based reagents which is used in organic synthesis. Okay, so this is what iron based reagents. So we are using some reagents in the organic synthesis which is having the iron as a component here, and the chemistry of this iron compound containing carbon and iron bond, chemical bond, carbon and iron chemical bond. It is used as a reagent in most of the organic synthesis, like some examples if you see. So this is what you can see, iron pentacarbonyl iron is there, or you can see CO9, that is dicarbonyl nonacarbonyl di-iron nonacarbonyl, or sometimes you can see disodium tetra carbonyl ferrate, that is your Coleman's reagent, that is your Coleman reagents. Okay, so this also we can see where it is mostly used in this iron organo iron catalysis. Okay, and it was first discovered in 1891, that is your pentacarbonyl iron. So from here you can see the use of organo iron catalysis started. This was by your Mond and Berthelot. Okay, so these two scientists discovered this pentacarbonyl iron. Okay, so in 1891, and you can see that this has happened to be a very useful working organo iron catalyst. Now if you see here the iron, so iron in its form, it's going to have the configuration that is of argon 3D4S0, 3D8, titanium, vanadium, chromium, manganese, iron 678. Okay, and this is 678. Yes, 3D 2 and 678. So you are having this as a iron here, iron, and usually this iron is always having in +2 and +3 as a stable oxidation state. Now if you see iron in +2 oxidation state, so it is going to have that of argon 4S0 3D6. So this is what. Okay, and if you see iron in +3 state, so you are having that of argon 4S0 3D5 state. Okay, so this is what about the iron here. But out of in this, so +2 and +3 state is very much important here. Okay, and usually these have the coordination number of 6, coordination number 6. Okay, with having the octahedral arrangement. So this is what about the iron. And if you see the iron, this is what about the iron 2, and if you see iron 3, that is 3d54s0. Okay, this has a possibility of coordination with the 3 to 8 ligands, coordination with 3 to 8 ligands to exhibit octahedral coordination here. And this iron 3 is somewhat hard acid. It is termed as a hard acid than iron plus 2. So, and that's why usually iron 3, it is going to always react with your hard base. This also you have to keep in the mind, like HSAB we say. So iron 3 is a hard acid, considered as a hard acid, and always it has the prone to react with the hard base in this context. And if you see iron 0, like in FeCO5, iron is in 0 state, oxidation state, and it mostly coordinates to 5 to 6 ligands with having trigonal bipyramid structure and octahedral geometry sometimes. And the best example for this is your Coleman reagent, that is your disodium FeCO4 minus. This is what, okay, Na2FeCO4. So this is what about the Coleman's reagent. And if you see the fascinating part of this Coleman's reagent, that is your reaction of nucleophilic Coleman reagent, nucleophilic Coleman's reagent with if you say 2 alkyl halides, you react this 2 moles of alkyl halides Rx and R-X, you take 2 alkyl halides, and if you react with this Coleman's reagents, so you are going to result in getting the ketones plus some byproducts. You are going to result by getting ketones and some byproducts via oxidative addition. So there is a very good oxidative addition, and also we can observe reductive elimination. Okay, so reductive elimination which is going to release some of the byproducts in organic byproducts with having some concerted mechanisms. Okay, in the concerted mechanism, so we have learned this concerted mechanism, SN1 mechanism, radical mechanism, ionic mechanism. So in this case this is having the concerted type of mechanism in which the oxidative addition and reductive elimination is going to be observed here. Now if you go for this one concept here of the addition, so we'll go for this FeCO4. Okay, so this is your Coleman's reagent, and when you add this with Rx, that is your alkyl halide, with oxidative addition, it is going to happen, and you are going to get this structure CO, and here is CO, and CO4 is there, so FeCO4 1 2 3 4. Now here is going to be added here R, so this is what, and you get minus charge here, and you are going to get Na plus here. So this is how the first step where we can see the oxidative addition of this is going to happen here, R here. Okay, now this is a one type of trigonal bipyramid TBP type of geometry is observed here. Now if you see now here, so very nicely you can see here, that is insertion. Now there is insertion reaction here, where you can see the R is inserted into this carbonyl group, and you are going to get something like this, C double bond O R. Now here there is CO 1 2 3 4, and this is what the vacant place will be there. So this is going to happen minus, and this is Na plus as usual. So where R is been introduced into this acyl group, C double bond O group here. So this step is insertion takes place. Now vacancy is created. Now that is been taken place by the L or solvent molecule, or you can take any carbonyl molecule also can take place of this vacant place to get this compound now. So CO is there, I will take it as a L here, CO, and this is RC double bond O minus Na plus. So this is what I'm going to get here. So I have added here the CO, and it becomes now penta coordinated 1 2 3 4 and 5 penta coordinated. It is coordination number 5 TBP type of this is going to happen here. Now is the best way to has become a good this one to add of the another halide, that is your R dash X, where you can see oxidative addition is going to happen here, and again you are going to get here. So this is your C double bond O R, so CO L is here, and here you can CO like this. Now here R dash is been added here into this. Again it becomes now coordination number 6, octa coordinated. And finally if you see that if you add one ligand here, and there is a reductive elimination where now this R dash is going to insert into this, and we are going to get in reductive eliminated product, that is your R C double bond O R dash. This is what ketone we got here, and finally the product will be the byproduct will be a FeCO3 L2, FeCO3L, and this is addition of one more L, so you are going to get L2 like this. That is your TBP type 5 coordinate like this. Okay, so this is a byproduct along with your required required product of the ketone. So this is how our Coleman's reagent reacts with this organic compound via oxidative addition, and where we are going to get the ketones here. So you can see here once again, so Na2FeCO4. Okay, so addition of R here, then first step, then second step is this is how oxidation, this is how the addition takes place here. Now insertion is going to take place where this R is inserted into here, so like this insertion takes place here, and finally again you can see there is a vacancy here created. Now there is the ligand insertion here, or carbonyl insertion here, so you can see here 1 2 3 1 2 3, and this is inserted L here. Now next step is what here, again it is going to react with R dash X here, so you can see here R dash is added here, again it becomes now 6 coordinated. Okay, so from this here you get 6 coordinated, and finally there is reductive elimination of this by this R dash is inserted in here, and you get ketone, and ligand is ligand, whatever the ligand is here we have taken, so again there will be one more ligand added here, and finally we get the byproduct of this. Okay, so this is how the Coleman's reagent is used in this process. Okay, so this is how it works on. So absolutely absolutely, so very important, and very important catalyst, organo iron catalyst I can say, which is widely versatilely used in organic synthesis very beautifully. So from this Coleman's reagent, so many products we will see in the next video. So what we can do from this Coleman's reagent here, and if you go for yeah, so I think that this video is extended now, so this is more than sufficient. So understand this concept of this organo iron Coleman's reagent, and addition of this R dash X. Okay, so 1 2 3 4 5, yeah, R is added here, so this is how it happens here. Okay, so addition takes place absolutely. So we'll discuss all this on the Zoom meet. If you have any doubt in this, you can make a point on this Coleman's reagent here. Okay, absolutely, it's addition. Addition takes place here, so we cannot say the oxidative type of addition, but addition is going to take place of R here like this. Okay, reductive elimination, addition, okay, coordination or addition, you can use the word. Absolutely, that will be fine here in this case. Okay, so hope you understood this concept of the organo iron here, followed by whatever in the followed by the carbonylation. So in the next video we will go for some of the most important reactions of the organo iron, followed by cobalt and palladium, so that we can, by this week we can end this unit 2. We will think of that. Thank you.